In this video, we're going to be talking about the instantaneous rate of change of a function and the definition of the derivative. And last time we talked about the average rate of change of a function, and we said that, for a given function, the average rate of change over an interval was kind of like, the slope between the 2 points. It was the slope of the secant, which gave us an idea of the behavior of the function over some sort of closed interval. But if you look at this graph, you can see that at the point where x equals a, the function's in the midst of decreasing. So this slope of this secant line might not, really capture what's going on right at the moment when x is equal to a. And if we wanted to find the, behavior of the graph as x went towards a, we might be interested in the slope of the tangent line. But we don't really know how to find that quite yet, right? We can see that this slope here of this line, if you can envision it being a line, that just touches at that one point where x equals a, that is going to really capture the, trajectory or the behavior of the function at the point where x equals a. So let's talk about how are we going to find the slope of the tangent line. Now, I said that when b was kind of farther over there to the right, it wasn't a very good approximator. So let's think about maybe moving that second point a little closer to a. Now, if b were to be right there, then the secant line would be about like that, and this seems to be closer to the slope of the tangent line than I was when b was farther out, but it's still not quite there yet. So let's move b really close to a. Now, if we draw the secant line in and connect these two dots, we can see that this is pretty close to what I had, suspected the slope of the tangent line was. And if I was to move b to be like, as close as possible to a, but as close as possible, what does that even mean? Then I might feel like I was getting as close as possible to the slope of the tangent line. So what we're going to be interested in doing is taking the limit of rise over run as run goes towards 0, right? I'm moving that b towards a. So this is the limit of rise over run as run goes towards 0. Now what we're going to find in this class is that oftentimes that limit is well defined. Okay? But let's go over and write this instead of limit as run goes to 0, rise over run. Let's write it a little more algebraically. So we're going to define the instantaneous rate of change of a function f at a point x equals c to be the limit as h goes to 0 of f of c plus h minus f of c divided by h. Okay, so let's go back over to my original drawing and think about what. Now back over here, okay, we're not talking about a and b anymore. What we're talking about is c and h. Okay, so what do we mean by h? It looks like we mean h is the run. So I'm going to just label that with h. I'm going to call this c, and therefore if I started at x equals c and I bumped up by h, this x coordinate would be c plus h. And then here, this y coordinate, this will be the y value of f, where x is equal to c. And then over here, it'll be the value of f, where x is c plus h. And so what we see is we are computing the limit of rise over run as run goes towards 0. Now, there's another form of this that you kind of need to be aware of. You need to be able to recognize these, but not necessarily able to regurgitate them at a moment's notice. So the other form, the limit as x approaches c of f of x minus f of x minus c. Okay, and, going back over to the other one, what this new one means is, okay, let me just kind of clear out all of this. It's still going to be a limit of rise over run as run goes towards 0, but I've got over here x, c, f of x, and f of c, and I'm still moving that x towards that c, right? I'm letting run go towards 0. So this is all the same. So for a quick example, a way that I said you need to be able to recognize this formula, they could ask you if f of x equals x minus 2 squared, there's a picture of x minus 2 squared because I think you're going to need that. What is the value of the limit as h approaches 0 of f of 2 plus h minus f of 2 divided by h? Okay, so first we need to unpackage. We know that the limit as h approaches 0 of f of c plus h minus f of c divided by h is the instantaneous rate of change of f at x equals c. So I'm going to say, actually, And we know that the instantaneous rate of change of f at x equals 2 represents the slope of the line tangent to the graph of f at x equals 2. So we can see, okay, at x equals 2, that's where it's really hitting its minimum, okay? It's the bottom of the parabola. And I think we can see that the x-axis is tangent to the graph of y equals x minus 2 squared. So I'm going to conclude that the slope of the tangent line is the slope of this horizontal line, and the slope of a horizontal line is 0. Okay, so I'm going to say that this limit is equal to 0 because that's the slope of the tangent to the graph, to that graph at x equals 2. All right, another quick example is if g of x is 4x minus 3, find the limit as x approaches 1 of g of x minus g of 1 divided by x minus 1. So I'm going to look at that limit of the difference quotient. I'm going to know that that is code for the slope of the graph of g at x equals 1. Okay, well, wait a second. I know that g is a line, and it has slope 4. So the slope of g at any x value is going to be 4. So I'm going to say that that limit is equal to 4. Now, before we move on, we need to talk a little bit about notation, because I've just been writing over and over again the slope of the tangent to the function at the x value, and we need like a shorthand for that, right? So I'm going to fill you in on some notation. So to represent that limit, right, which is the limit of rise over run as run goes to 0, which represents the instantaneous rate of change, represents the slope of the line tangent to the graph at a given x value, we're going to call that f prime of c. Okay, and again, just to be clear, that's an apostrophe, and we read that as prime. Or we could call it dy dx at the point where x equals c. Really, you'll see both of those throughout this course. So going back to my earlier two examples, I would say that here, f prime of 2 equals 0, and g prime of 4, g prime of 1 is equal to 4. Because the slope of the tangent line at x equals 1 is 4. Now let's talk about the word differentiable. Okay, we're going to define the word differentiable to mean that the derivative, pardon me, you don't know that word yet, that the instantaneous rate of change of a function f at an x value a exists. And remember, f prime of a is itself a limit. Right? So the limit is h approaches 0 of f of a plus h minus f of a divided by h. So we need that limit to exist in order for the function to be differentiable. But for the most part, most of the functions we know about in this class, they're going to be differentiable almost everywhere. So it's going to be easier for me to show you examples of places where a function is not differentiable. Now, the ways a function cannot be differentiable are pretty much equivalent to the ways that that limit can non-exist. Okay, I'm going to start off with, the limit of rise over run as run goes towards 0 doesn't exist between disagreement and one-sided limits. And I think the easiest way to look at that is to just say, okay, over here slope is positive, and then suddenly, I'm going to just have like a line segment with a negative slope. Over here suddenly slope is negative. And there was never a place where it was, nice and flat, right? We've got that sharp corner. And so that's what you're going to find is that, that's the instantaneous rate of change instantly going, probably not the right word, but suddenly going from positive to negative and not going smoothly. And we'll call that a sharp corner. Next, we could have that limit non-existing because it was going to infinity. And that's going to be a vertical tangent. And that doesn't happen super often, but one example of a place that it does happen is y equals the cubed root of x. That comes up, and it goes. Really, this is related to the fact that the graph of y equals x to the third has a horizontal tangent at the origin. And this is not not my best drawing ever, but if you go and you just graph y equals cube root of x on your own, you'll find that it has a vertical tangent at the origin. And the last way a function could be not differentiable is at any place that it has a discontinuity, it won't be differentiable, because remember that f prime of a represents the slope of the tangent line. Okay, and so if I had, say, a jump discontinuity, it's like, well, where would I even put a tangent? There's no place to put a tangent, right, because we can't put it on both pieces. It just doesn't make sense. Okay, I could have a vertical asymptote, something like that, and you couldn't have a tangent line there because, again, there's no graph to put the tangent on. And again, over here, like a removable discontinuity, again, there's no place to put a tangent, so there's not going to be a slope of such a tangent. Now I'm going to tell you that any place that you find that a function is differentiable, that automatically means that the function is continuous. Now, just like immediately, I want to point out that the converse of this does not hold. I just drew you two pictures of situations where the function was continuous, but then it was not differentiable. And let me actually go back and point. So on the red graph, it's continuous here at this point, but it is not differentiable there because of the sharp corner. And on the blue graph, we are continuous through the origin, but is not differentiable because of the vertical tangent. So continuity does not give you differentiability. But if we can lay in a tangent line, then it definitely means that the function is continuous. Now, the proof of this theorem is really nice, and it uses the definition of differentiability and continuity at a point, but I'm going to just kind of flash it up on the screen and run through it real quick. And if you're interested in the details, I have a separate video of this proof. All right, so we're going to start off by supposing that f is differentiable, right? If f is differentiable, we're trying to show it's continuous, so we're just going to suppose that's true. And that means that f prime of a is well-defined. It's a real number. And we want to show that the function is continuous, which is to say that the limit of the function is equal to the value of the function, at the point we're interested in. But we could also show that the difference of those two things is zero to have the same effect, right? To show that it's continuous, we could show that the limit as x approaches a of f of x and f of a have no difference, right? So we're going to start off by considering the limit as x approaches a of f of x minus f of a. And then we're going to multiply by a clever form of 1, right? We're going to multiply by x minus a divided by x minus a. And that's okay, right? We're not multiplying by 0 over 0, because we're considering the limit as x approaches a, which is what happens when x is near a but not equal to a, right? So this is not 0 divided by 0 that we're multiplying by, so this is fine. And then we use a property of limits that, provided that both limits exist, the limit of the product is the product of the limits, okay? And then the big thing that we need to recognize is that this is f prime of a. And we said that f prime of a is just some real number, okay, because f is differentiable at a. So any real number times something that's going to 0, like x minus a as x approaches a, number times 0, that equals 0. So I showed that f of a and the limit of f as x approached a had no difference, which meant that this equality was true, meaning that f is continuous at x equals a. All right, so now let's talk about the derivative. Okay, the derivative of f of x is a function that gives the slope of the tangent line to the graph of f at any x value. Okay, and we call that f prime of x. Okay, and our definition is going to be very similar to the instantaneous rate of change of f at a point. It's just going to be at, again, the limit of rise over run as run goes towards 0. But this time, we're just going to leave x as unspecified. And for the most part, this limit can be computed. Okay, sometimes actually computing it is a little difficult, but for this limit for the functions that we deal with will be able to be computed at least at most x values. And before I move on, I should probably point out to you that f prime of x, we've got another notation. This is the same as just dy dx in general without some sort of specified x value. Okay, these mean the same thing. F prime of x, dy dx. Usually if we start off with a function f and we want to take its derivative, we'll end up with f prime of x. And if we start off with y equals, some expression in terms of x, then our derivative will be dy dx. All right, so here's a couple of quick examples to develop a couple of quick derivative rules. If we have y equals 2x plus 1, then dy dx is the slope of the tangent line to the graph of 2x plus 1 at any x value. So let's just go ahead and draw a picture of this. Since y equals 2x plus 1, that's a line. A line has the same slope everywhere. Okay, so the slope of this thing is 2 at all x values. Okay, so dy dx is a constant. Okay, now and maybe I'll talk about the derivative of the constant, and then I'll talk about the general rule up to the side. So if g of x is equal to 10, well, we know what that graph kind of looks like. If that's 10, g of x equals 10 looks like that. Right? It's a flat line. And we know that a flat horizontal line has 0 slope. So that means that g prime of x is always equal to 0. So what I'm going to conclude from that, if we take the derivative of something that's linear in x with respect to x, and that's what that d dx is representing. It means take the derivative of, which is a thing that we're going to be doing, repeatedly in this course. So if we go to take the derivative of a times x, where a is some number, that's going to just be that number. I guess, and you can see that the derivative of a constant is going to be 0. Now, the fact that they had that 2x plus 1 and the plus 1 didn't change the slope, well, I might let you think about what that means. But that's just a couple of rules that we'll go and kind of select lesson. All right, and this is a pretty common type of question for us, especially, when we're first beginning. Now, I'm going to actually change this first function f. I'm going to extend the graph a little bit to recover back up from the left edge and go back down off of the right edge. So I'm going to do that real quick. Because what I want you to do is I want you to start with, when you're looking at the graph of a function and you're going to try to sketch the graph of its derivatives, I want you to start with the places where the tangent line is horizontal, right? Here, the tangent line is horizontal, there, here, there. Because these are the places where the derivative is 0, right? Because the derivative is the slope of the tangent line at any x value. So I'm going to kind of just mark these off on my horizontal axis. Whoops. Yep, I'm still in the shot. All right. So then I'm going to kind of copy these down here. And since, the height of the graph of f prime represents the slope of the graph of f. So since at these red places, the slope of the graph of f is 0, the height of the graph of f prime needs to also be 0. Okay, so these are zeros of the graph of f prime. Next, I'm going to identify the intervals in which the slope of the tangent line to this function is positive. And I'm seeing over here, positive tangent line slope. Over here, positive tangent line slope. And really for everything, as the function is increasing, which is a word we'll talk about later, we're going to see positive slopes. So I'm going to see over here, I've got positive slope, and through here, I've got positive slope as well. Meaning that the graph of f prime needs to be positive. It needs to be above the x-axis. So it's probably going to look like that, because I know it has to return back to 0. Right? And we don't really know the shape or the relative heights of these things. And, especially since it's a hand-drawn thing anyway, there's no way we could really tell. But we do know that it's going 0, positive 0, and then between these, it sure looks the slope of the tangent has gone negative, but then it recovers back to 0, so it's just going to be like that. Okay? And that is a suitable sketch of the derivative for the level that we're at right now. Okay? On the next one, it appears that on the first piece of graph, we've got a line segment that has a constant positive slope, all right? And so I'm going to say that this is a constant positive number until, whoops, that doesn't look all that horizontal, okay, until we hit that discontinuity. Now we know that at a point of the derivative is undefined. It does not exist because the limit, or there's no way for us to lay in a tangent. So we need to have f prime undefined at that x value. But then, we're going to see that after the discontinuity, the slope is positive. Now, I'm going to that this slope right here, right when we first pick up, is significantly less than the slope, of that line segment where we left off. So I think we're going to pick up lower. But then you can see that the slope is kind of increasing, right? It's getting steeper and steeper as I move to the right. So I'm going to need to see f prime, and that's what we're seeing here. But again, since we've got that discontinuity, it's not differentiable, means the derivative is undefined. Okay? And so that's a suitable sketch. Now the right side of my derivative, this segment right there, I don't know. You don't know yet at this point whether it's going to be, an upward sloping line or whether it's going to curve up. You don't really have the tools to determine that yet. Now let's go the opposite direction. Let's start with the derivative and sketch the graph of the function. All right, I'm going to give myself a little more room here so I can make sure I give you a good try. Okay, so starting with the one on the left, the derivative is going, it looks like a line segment, or a line. It's going from positive to 0 to negative, which means that the graph of f goes from having a positive slope to a 0 slope to a negative slope. Okay, so something like that. Okay. And hopefully the 0 slope was happening, at the point I had marked. It looks close enough. Because again, we've got positive slope. We've got 0 slope at the top, and we've got negative slope along the way down. Okay? We don't know, though, where that graph sits with respect to the x-axis, right? Is f positive? Is it negative? Is it sometimes positive and sometimes negative? We don't have any information to dictate that, right? All the derivative is telling us is, what's the function doing? Is it sloping up or is it sloping down? Okay, but that's all we can tell. So, it might be the case that it looks like that. We don't know. We don't have the information to tell that yet. Okay, for this one, I've got positive, 0, negative, negative to 0 to positive. Okay, so that means that the function needs to have a positive slope and then a 0 slope, then negative slopes, then 0 slopes, and then positive slopes. Okay, so I've got positive to 0, negative slopes back to 0, and then positive slopes. But I didn't probably line that up just right. So let me show you how I'm going to do that. I'm going to kind of trace down to the 0 spots. So basically that's what I was aiming to go straight down from there, and I'm going to aim to go straight down from there. But this is very approximate. And so I'm going to make sure that these are the places where, I have 0 slope. So I'm going to have positive slope before here, negative slope, and then positive. And, we want that to be nice and smooth. Not a sharp corner, right? Because if that was a sharp corner, we would see that f prime failed to exist. Okay, that's a suitable drawing for where we are at this point. Okay, now this next example, I'm going to need to draw a picture, right, in order to find out these things, because we don't really have any derivative rules yet, especially not involving like an absolute value. So I need to just kind of draw a picture here, and we can look at the slopes of this function. So 1 minus x plus 2, I'm going to need more room. So I definitely didn't need that much like in the positive x-axis. Maybe I'll just draw it like that. Okay, and I'm going to let 2 squares represent 1 unit. So this will be 1, this will be negative 1, that will be negative 2. So, and I don't really expect you to be able to graph this at a moment's notice, but what this looks like y equals the absolute value of x, but flipped upside down, moved to the left by 2 and up by 1. Okay, so I know how to draw this. That's a decent sketch. Okay, if we want to find the value of f prime of negative 5, what we're interested in is the slope of the graph of f at x equals negative 5. But I can kind of see, I don't have all the way to negative 5, but I know that, to the left of that sharp corner, I've got myself a constant slope, and that slope's 1. So I'm going to say that over here, f prime of negative 5 equals 1 because that's the slope of f over there to the left of negative 2. At x equals 0, that's right here, I can tell what the slope of f is. The slope of f at the point where x equals 0 is negative 1. And then at x equals negative, I've got this. I've got myself a sharp corner, right? I'm going to say that's a sharp corner. It's actually one of the few things that you know of at this point that has a sharp corner. Okay, I'll just tell you right now, y equals x to the 2/3 power also has a sharp corner. But I'll say that f prime of negative 2 does not exist, basically due to that sharp corner right there. Okay? And so that's one way that we could find values of derivatives at this point, not knowing any real rules yet. Now I'm going to show you how a person would compute the derivative of a function using the limit definition if they absolutely had to. But I'm just going to kind of flash it up on the screen and tell you that we're not actually going to have to do that in this class. We only have to recognize the limit of the difference quotient, meaning the derivative, then we can apply our rules. Okay, we're big on the rules in this. All right, so I'm starting here with the definition of the derivative, right? G prime of x is the limit as h approaches 0 of g of x plus h minus g of x divided by h. Okay. Then up above, I just kind of wrote out what is g of x and what happens when I plug in x plus h into g. Okay. So then I substituted on g of x plus h and g of x. And then here, you'll see I distributed x plus h times x plus h. I used FOIL, right? And I get x squared plus 2 times x plus h times 2 times x times h plus h squared minus the original x squared all divided by h. Okay, so I, subtracted these. They went away. Then I factored out an h from the numerator because I had an h in both terms, and I could cancel those terms off, and I was left with a 2x plus h as h went towards 0. As h goes towards 0, that's going to go towards 2x. And so I'm going to conclude that g prime of x is equal to 2x. Okay. Honestly, for almost every other function, that computation right there is much less pleasant. And that's why we don't do it in this class. This is just AP Calculus. This is not an analysis class. This is not like the most hardcore calculus class ever. So we're not going to spend a whole bunch of time computing derivatives using the limit definition. That's just not going to be useful. Okay, an equation for the line tangent to the graph of g at x equals 3. Well, I can write down the slope of the line tangent. I don't know what keeps doing that. Hold on. All right, set there. So slope of tangent is equal to g prime of 3, which is going to be 2 times 3, which is 6. Okay, so at the point where x is equal to 3, the slope is 6. Okay, and then the point of tangency, again, sliding all around. Okay, the point of tangency, I'm going to find by saying it's going to be x equals 3 and y is equal to g of 3. But g takes a number and squares it, so that's going to be 3 and 9. And now that I've got myself a slope of a tangent and a point that the tangent runs through, I can use the point slope form of a line. Maybe you forgot about that from Algebra 1, but that's going to be the form of a line that we're going to want to use in this class because we're always just going to want to get a slope from the derivative and get the point from the original. And so we're going to say y minus the y coordinate of the point we know is equal to the slope times x minus the x coordinate that we know. And that's the equation for the line tangent to the graph of x squared at the point where x is equal to 3. Now, you could distribute the 6 and add over the 9 if you wanted to, but it would kind of just be like you're risking making an algebra error, and you're also wasting your time. We're perfectly fine to just leave it in point slope form in this class. The last example I got for you in this video is going to be, really just back to what do we mean by these, function notations? What does h of 1 mean, and what does h prime of 1 mean? Okay, and what does it mean for a line to be tangent to a graph? So we're going to start off with h prime of 1. H prime of 1 is code for the slope of the line tangent to the graph of h at the point where x equals 1. But I know that the slope of that tangent is, I can see it. So I conclude that h prime of 1 is equal to 2. Okay. Now to find h of 1, I need to think about what does it mean for a line to be tangent to a curve. It means that they have the same slope, but also the same y value. And we know how to find the y value of the tangent line at x equals 1. Y is going to be equal to 2 times 1 plus 3, which is going to be 5. Okay? And we know that at the point of tangency, they have the same y coordinate. So that means to me that h of 1 is equal to 5. And that's going to be all for this video, I think. I think I had originally planned to talk about the mean value theorem in this video, but I'm already over half an hour, and I'm just going to record that.